All right, welcome back, everyone. Today we're going to start chapter 5 of Pinter's book. And chapter 5 deals with subgroups of a group. And a subgroup is kind of what you probably think it is. So if we have a group G, let's use multiplicative notation for the operation on G. Subgroup of G is a subset of G, which is also a group. In particular, it has to be a group under the same operation as the group operation on G itself. So what does this mean? It means that S contains the identity element of G. It means that S is closed under multiplication. And it means that S has inverses. And so if you just pick your favorite set, like, our favorite group, we pick our favorite group, maybe the integers with addition. Well, if I pick some random subset, the subset consisting of, I don't know, 4 and 7, that's very, very, very far from a group. It's missing an identity element. It's not closed under anything. I mean, you can talk about adding elements, but it's kind of silly to do so. This is just not even close to a group. On the other hand, often it's not so hard to come up with examples of things that are groups. We could use this notation, 2 times z, to mean elements of the form 2 times n, where n is in z. In other words, these are numbers divisible by 2. This is a perfectly good subgroup of Z. When we want to talk about subgroups, we're going to use this notation. This expresses the fact that 2Z is a subgroup of Z. I guess I should have written it more like this to make it a little bit clearer that it's the blackboard Z. Sorry about that. But in any case, this is a perfectly good subgroup. And many other kinds of subgroups appear in mathematical nature by taking a situation where something is already a group and restricting your attention in that group to a certain kind of element. That sounds pretty vague. Let me show you a specific example that I have in mind. Let's look at functions R to R. These form a group. In particular, the group will be under addition, so we'll use additive notation. Let's check really quickly. First off, is it closed under addition? Yes. Given two functions R to R, f and g, we can define a new function f plus g as a function by writing this as take the value of f at some x and add it to the value of g at some x. This might be a little bit unusual notation, like we don't write this very often, but we can think of it as f plus g as an abstract object is a function which eats an x and returns a number according to this formula. This makes addition an operation on functions rather than on the individual numbers, which is what this over here means. Because normal number addition is associative, that gets us that function addition is also associative. By just checking it element by element. There's a zero element, a neutral element. The neutral element satisfies f plus 0 equals 0 plus f equals f. And what is that function? It's the 0 function. This is a little bit weird notation, but when I write 0 of x, I don't mean 0 times x. I mean the function 0 of x, which is the constant function 0. In practice, that means the same thing as multiplication because anything times 0 is 0. But I'm really trying to distinguish between thinking about this as multiplication and thinking about this as a function because I'm only talking about functions R to R as a group. So there really is no multiplication under consideration here. Let's see. The last thing we have to check is the existence of the inverse. Well, since we're dealing with addition, the inverse is the negative of a given function. So we have minus f of x equals negative f of x for every x. And so in particular, f plus, oops, sorry about that, f plus minus f of x. Well, according to my first rule, I evaluate that by f of x plus minus f of x. This is the same thing as f of x plus negative f of x, which is f of x minus f of x, which is 0. And since this is true for any x was arbitrary, that means this is the constant function. And so f plus negative f of x gets me to the neutral element, which is what I wanted to find. Properly speaking, in order to completely do the verification, I should also do it the other way around, right? I should do minus f plus f. I'll leave that to you guys to check. The verification is basically the same process, but just with the minus sign slightly rearranged. Okay, so the reason I like this example is because what I was saying before is that subgroups can come about via, let me write this down. Subgroups can be found by asking for properties compatible with the group operation. So let me give you some examples using this function notation stuff that we've been talking about. So if I look at the collection of functions as a group under addition, this is a huge group, right? There are all kinds of crazy functions in here. Because when you guys think of functions, you probably often go to standard nice examples like polynomial functions or, maybe continuous functions. But as we know from our calculus, the sum of two continuous functions is continuous. And so because I just went to all this trouble to check that functions have all these nice properties, continuous functions are essentially automatically a group themselves because they are a subset of the collection of all functions which have these properties. Okay, I wrote multiplication because we were using multiplicative notation above, but because the sum of two continuous functions is continuous and the negative of a continuous function is continuous, that means that continuous functions are a subgroup. The same is true for other calculus collections of functions, like differentiable functions, integrable functions. We said before, polynomial functions. If you guys know linear algebra already, one class, another important class, a subclass of the polynomial functions are just the linear functions. Really, any other degree is also okay, as there are many such classes of these guys. And all of these will naturally be subgroups. And so when one wants to show that something is a group, sometimes it is helpful to, instead of showing that it is a group from first principles, you can show that it belongs to some larger class of things and that they have some property which is compatible. And essentially, that's what we've been doing when we teach calculus, right? We explain that continuous functions, sum of two continuous functions is continuous. What we're saying is continuity is compatible with the function addition. And so we get to inherit this property for free.